Okay, hi folks. So in this video, we're going to be drawing mathematical models in Desmos. So remember in class, we performed a very simple experiment. We took a tennis ball and we rolled it down a slope. And we changed the distance that it rolled down the slope. That was our independent variable. And then we measured the time it took for it to do that. That was our dependent variable. And it's pretty much common sense that, when the ball rolls a longer distance, then it takes longer to do that. So there's a definite trend, but what's not so obvious perhaps is, well, what is the exact mathematical equation that accurately describes this? Because we want to understand reality in more detail. It's not enough just to say, oh, that time increases when distance also increases. We want to know the exact mathematical expression that describes that trend. So that's what a mathematical model is. And really, science is all about these models. They play a very important role. And here's one example of a very important model that everyone's talking about these days, these years, these decades, and that is a climate model. So we have a lot of climate scientists who collect a lot of data about the climate, and then they try and build models that can accurately describe how the climate works. And if you have an accurate model that describes all the data we can collect, then you can also use that model to predict what will happen 10, 20, 50 years down the road. So we can predict what the climate is going to look like. One set of data that the climate scientists look at is the carbon dioxide concentration in the atmosphere. And here are measurements for the past 2,000 years. And you can see how the level of CO2 remained pretty much constant for a very long time. But then in recent centuries, since roughly the 1800s, the level of CO2 has increased dramatically. This is called the hockey stick curve. Looks like a hockey stick, sort of straight for a long time, and then suddenly it bends upwards. And why? One obvious question is, well, why is the CO2 concentration increasing so much? Well, luckily, we know some chemistry, and we know what happened. Let's just go in and look here at. You can see how it was around the 1800s that the level of CO2 really started to increase quite a lot. And we know that in the 1800s, we discovered fossil fuels underground, coal, gas, oil. We started to dig all that up on a massive scale, and we started burning it in all our steam engines we had invented. And that's really what kickstarted the Industrial Revolution. And that is also what underpins our modern societies, the burning of fossil fuel. And we know the chemistry of fossil fuels. We know that it's made, coal, gas, and oil, a lot of carbon, hydrocarbons. And when we burn that, we know that we produce CO2. For every gram of fossil fuel that we burn, we produce around 3 grams of carbon dioxide. So, and since we know, we have kept track of, we have measured, how much coal, oil, and gas that we have been burning, consuming for the past 200 years, you can see how the rate of use has increased dramatically in the past 200 years. So we know how much we're burning, so we can actually make a prediction about, well, how much CO2 should we be emitting into the atmosphere. And when you do that calculation, you get a perfect correlation. You can see how we can predict that the levels of CO2 should be increasing along this red curve, and we can actually measure that the CO2 concentration is going up according to that curve. So we are 100% sure that the levels of increase of CO2 that we see is due to all the fossil fuels that we are burning. Then you might ask yourself, well, what's the problem with that? Well, the problem with that is we have also measured the average surface temperatures on Earth, and we have been doing that also for centuries. And we can see that the average surface temperature on planet Earth is actually increasing. There's again a trend, a very obvious trend, clear trend of the temperature increasing, as you can see. and we know that that actually correlates with the rising levels of CO2. And that's because we again know the science of carbon dioxide. We know that it's a gas that traps heat, it traps infrared radiation, so that when the levels of CO2 go up, well then the surface temperature is bound to go up as well, and you can see how they correlate well together there. So yeah, mathematical models, they play a very important role in our understanding of reality, and that's why it's important to learn about this. Try and find a mathematical model for our data set. Now, let's pretend we have no idea what the equation should look like. So we're just looking at our data, and we want to try, something relatively simple. So you could look at this and say, well, maybe a straight line describes our data set well. So why don't we try to model this against a straight line? So what's the equation of a straight line? It's y equals ax plus b. So in Desmos, we write y1, our dependent variable, and then tilde, use that wavy line symbol, and then we write ax1 plus b. So we simply input the equation of a straight line in this way, and then Desmos produces the best fit straight line describing that data. So in this context of modeling, the a and the b, the constants here, are called parameters, the slope and the y-intercept, and Desmos gives us the values of those. Desmos also gives us the r² quantity. So the closer this is to 1, the closer the data points lie to the graph. So in some sense, the closer r² is to 1, the better the fit is. But that's not all we rely on when we look for a good mathematical model, because we also need to take our uncertainties into account. We also need to take the context of the experiment into account. So it's not enough just to look at the r² quantity. And let's see what's wrong with this straight line model. So the first thing to see is that the graph doesn't go through some of the windows of uncertainty. So remember, we've drawn our error bars here, and we can see that, the straight line doesn't go through this window over here, it doesn't go through the error bars, so this data point is not accurately described by that model. Okay, some of the others are, but then you can see it misses again this window of uncertainty, it even misses this big window of uncertainty, so it just passes it. And that one's okay, and then the last one is also being missed. So 4 data points are actually not accurately described by this model. So this is not a good model. And looking a little bit more carefully, you can also see that the data set sort of is slightly curved, right? It's a little bit curved. That's why it's the first and the last data points that are not described very well, and some in the middle there. So a straight line doesn't sort of capture that curvature very well. So that's not a good model. Another reason this is not a good model is look at what it predicts about distance equal to 0. It's saying that, it should take a tennis ball half a second to roll down a distance that is 0 centimeters. That doesn't make sense. So we're probably looking for a model that goes through the origin. Okay, so we're going to discard this model. It's not a good description of reality. So do we know something that curves? Well, you guys know quadratic functions. Here's a quadratic function through the origin. Still misses quite a few windows of uncertainty. At least it sort of gives us some sense of a curvature. But what's wrong with this parabola is that it suddenly starts going down again, which doesn't make sense at all. It means if we extrapolate to longer distances, then it doesn't make sense that it should take 0 seconds for our tennis ball to roll down 190 centimeters. That doesn't make sense at all. So it's like overall a quadratic model also doesn't seem like a good model to use. Notice that I can actually make a quadratic go through all the windows of uncertainty. So if I just use sort of a general quadratic like this that doesn't go through the origin, then I get something that seems to be a very good model, the R squared quantity very close to 1, but again, this model fails for other reasons. So you cannot, you have to take everything into account when you are deciding whether a model is good or not. What other curves do you know? Your 11 students, they are crazy with exponential functions, our hockey stick curves. Okay, they do play an important role in many areas of science, exponential curves, but this is definitely not exponential growth. Well, there are many other different expressions that you can think of. Here we have sort of an exponential that looks like this, that sort of grows and then levels off. And again, you can see how this model accurately fits all my data points in the sort of range 10 to 100 centimeters, but it doesn't make sense that after, when I increase the distance more and more, that the time it takes should level off to some constant value. There's an asymptote here. That doesn't make sense. By the way, I'm holding shift down and dragging the axis here to do this. Easily rescale the axes. Okay, so that model also fails. So what do we do? It seems like we're not successful here finding a good model. Well, Isaac Newton comes to the rescue. What we're going to be learning in this course is his laws of motion. And according to Isaac Newton, we actually know that the time that the tennis ball takes to roll down a certain distance, that time should be directly proportional to the square root of distance. That's what Isaac Newton tells us. So why don't we try that? Some constant times the square root of distance. And here we finally arrive at a satisfactory model. So not only does it go through the origin, not only does the time continuously increase as we increase distance, that makes sense, we also have a model that goes through all the windows of uncertainty, so it accurately describes all our data, and it even fits with the theory that Isaac Newton laid forward to explain motion. So there we go. We have finally found our model. Last thing I want to say is when you want to export graphs like this and put them into your lab report, then it's a good idea to maybe first just write out the equation as I'm doing it now. Then we can sort of take away the model there, and the advantage of that is you can actually change the appearance of your graph a little bit more. For instance, the line, you can make that a bit thinner, can easily change the color and so on, so you can get a nice graph. Okay, when you want to export it, do not just screenshot, go up here and export the image, and you can export a nice PNG that goes straight into your lab report.